Hi, my name is Dionisio and I'm the CEO of J, the easiest way for developers to build AI applications. So I'm glad you are here today with me, and we'll showcase a very nice Similarity Search demo for the fashion industry. But first, this is really quick end-to-end overview of what J is, which is the end-to-end coverage of the machine learning lifecycle. So J takes care of the entire lifecycle of machine learning from your raw data, which is local in your computer, then transform it into vectors, processes, extract its semantics, and then gives you an endpoint so you can query for similarity or query for predictions depending on what model you just created. So J really takes care of model tuning, data understanding, which is kind of data normalization, preprocessing, validation in some sense, and J also automatically trains your model, hosts it on, and delivers it via a scalable and secure API, either via REST or via language specific SDKs. Right now we only have the Python SDK, but there are more coming. So keep tuned. We'll have very good news in the short future. But right now, so another thing that is very important to say is J is based on three core API calls, which is Jfit, JSimilar, and JPredict. So in this demo, we'll be showcasing the Jfit, and the JSimilar will not be using the JPredict, as we'll not build any supervised models in this demo. We're only building this preprocessed text model for using the JSimilar for performing the similarity search. But it's nice to know that the whole complex machine learning thing, we are really working hard to abstract away in the few API calls as possible. Right now it's only 3. We expect it to keep being 3 in the future. So here are our main goals for this demo. We want you to get your J key and environment up and running. We want you to also be able to build a fashion similarity search application that can be integrated anywhere. So of course, if your similarity search, if your similarity engine is running on the cloud and it's available via REST API, of course it is able to be integrated anywhere, right? You can integrate in your web application, JavaScript. You can call it, in your C# app, in your Python, and it really doesn't matter. You can even, which I think is very powerful, you can even plug it into different no-code tools like Bubble or Adalo or Airtable, which is makes machine learning and J very powerful to extend. So you can also, we'd like you to also understand the core Jfit and the JSimilar methods, and be able to use REST API to query similar items using the JSimilar, and in the REST API. So the first thing is it's really simple to install and import J. You can install the J SDK by performing a simple and standard pip install J SDK, just like here. The only constraint, I guess, is that J requires Python at least 3.7, which at this time is really standard. And then we import J by doing from J import J. And now that you have J installed in your computer, you need to generate your J account, to generate your authentication key, which is free and is free forever. So you can do this inside Python, or you can do it by going to our website, getj.com, and just fill your email on the form there. But you can also use directly here in Python, like we're doing here. So j.getAuthKey, You give us your email, your first name, your last name. The company is optional, but it's nice to say where you work. And here, this is the response to a 1. It means it worked, and you now can check your email, and your authentication key will be there. After you do that, after you get your auth key, you can just use it here and say J. So we like to. This is our standard way of interacting with J. We just call it J, and then J equals J. And we say this is our auth key. Auth key equals the string that you just received in your email, and you're all set. So this is your J environment. You're now able to talk with the J server, and we know it's you, and we can show you your collections, and it's all fine. For this demo, we'll use the fashion dataset. So the fashion dataset, it's a very standard data set for benchmarking, similarity search, and also doing some recommendations engine. So there's a lot of very interesting tasks that we can try and test with the fashion data set we're using here. It's hosted on our Azure storage, so we're just loading here with pandas. And just taking a look at the full table data. So the fashion data set has table data with its attributes like the gender, the master category, article type, base color, things like that, and the product name. And it also has separated set of image that relates to these items on the table. So right now we work only with the table data. In the following demo, we'll also work with image, so J can process any kind of data, table, text, documents, images, everything that can be processed and turned into vectors. J can work with with the very same 3 core API methods. But we'll only work with the table data, and particularly with the text data from the product display name column. So we're just taking a look here of the full data frame. And as I said, for this demo, we'll only work and send to J the product display name data. So this is it. So you can see the thorough check, man navy blue shirt, the Peter England man party blue jeans, watches. So this is the full range of fashion items, I guess. So there are pants, there are shirts, watches, earrings, fashion stuff, right? So just taking a look here. And so the first thing that we want to do when we were working with J is send data to J. And sending data to J, differently from other platforms or other products, it's not really just sending your raw data and storing it in some kind of storage collections on J. So when we send data to J, it actually gets transformed into something else, which is for J, the vectors. So we're right now, when we send data to J, we're also thinking, well, what do I want to extract from this data? So if right now, in this demo, we'll be sending this text data, which is the product display name. So it's the product name, actually. And, well, we want to extract semantics, right? So we want to read Titan Woman Silver Watch, and we want to extract and store the meaning of this product name. So we want to store, it's a watch, the color is silver, it is, for women, and the brand is Titan. So this is a whole lot of information that we want to extract and store, and it is much more efficient. And I think this is the key why J works so well. Storing this extracted, synthesized information about something, it's much more powerful for the machine and for downstream tasks than storing the raw data, than storing the raw string. So J isn't substituting your own SQL or your own traditional storage where you're just storing your raw data and the product name. So you should keep that, right? You should keep your traditional SQL database, and besides that, storing the processed, the rich vectors in J. So when we are performing, we're now performing the Jfit, and we're sending this raw data, the product name, and we're converting it into a vector collection, and you will see why. But just a bit before that, just let me tell you that we have two different kinds of collections or DB types on J. We have the pre-trained and the trainable. So the pre-trained, it's basically the DB type, the image and the text, where we leverage huge pre-trained models such as ResNet for vision, the VGG, or basically any transformer model from Hugging Face such as the Bird, Roberta, and other cool pre-trained models that are hosted on Hugging Face repo hub. So the pre-trained ones are the ones that are of course, like the name says, they are pre-trained, and you send your data, and we use those pre-trained learned weights or learned network to extract, to transform your raw data and extract those vector embeddings from these huge pre-trained networks, and then we store those vectors. And the trainable DB types is where you send the data, and we learn a whole new architecture, we learn a whole new model, and then we extract those features and store them on J. But this is just to say this is a little bit of difference on how can you use J collection. So right now we're using, we're just extracting meaningful semantics, meaningful vectors from the raw text data, which is a product name, and storing it on J. So this is the Jfit method. Every time you run a Jfit, you create a collection. That's key. So you're running a Jfit, you're creating a collection of vectors, and every collection of vectors can be queried using JSimilar. And if it's a supervised model, you can also use the JPredict. So right now we're running the DB type text on just the product name column of the fashion data set. And here I just want to notice that we are using a specific NLP model. So I just enter in the sentence transformers page and look at what is the best model for semantic similarity search, and they have a very nice benchmark table there, and this is the best model. So it's all NPNet based V2. This is the best model for comparing sentence. So basically a sequence of words that's a sentence, and it's the best one for comparing them. So that's why we're using it here. If you don't specify any different NLP model, for default in the text database, the text collection, we are using the Distill Roberta model, which is also a very, very impressive NLP model. But anyway, so we're running the Jfit here. So J gets your raw data, your raw product name data, sends it to J. This model is already there. So this model processes your data, transform it into vectors, extract it from the network, and store it in a very efficient vector database. So basically that's all. We're saying this is the name of the collection. So every time after this that we want to query items or do something about this collection, this is the key. This is the name that we want to send to J, and we'll identify our collection. This is the collection name. Here's the data. We're sending the standard pandas data frame. It's interesting to notice that the index of the data frame, or if you send a column named ID, this will be the main key for your vector. So if you're going to use it afterwards or you're going to query, this is the ID that you're going to use to identify your product. So in this case, when we say to J, the ID 39386 is going to relate to the vector related to Peter England meant party blue jeans. So it's very important to keep in mind that J won't store your raw data, right? So J won't store your product name in this case. We will only store the IDs and the vectors related to your products. Okay, so running Jfit, we basically create this collection. So you can see here, so it's already run. It should take you some 10 minutes to run, maybe less, depending on if the machine's already up. And then we can check the created collection. So you can use the jinfo method and to query. So to query your all the collections that are hosted in your subscription, so that they are related to your auth key. So we are using jinfo. We're taking a look here. So this product display name standalone, which is the name of the collection that we have just created. It is of the type text. It has been created or modified in this date. And this is the size. The size is the number of vectors, of items that were inserted in your collection. So in this case, 44,000, which is precisely the number of rows in our data frame. So this confirms that each one of those products then became a representation, a vector inside J. But what does it mean? Well, we'll show you. And just before, if you want to retrieve your IDs for any reason, you can just use j.ids, use your collection name, and you can retrieve it in a simple method, just to take a look at it, or you can retrieve the exhaustive complete list by using mode equals complete. So this is the first 5 IDs that were inserted into J. Okay, so this step is actually optional, but I'd really like to show you because it really enlightens and how J is operating and why this is so interesting to work with, particularly this vision of transforming your raw data into vectors. So the first thing is that you can always download your generated representations, your generated vectors. You can always do that by performing j.download vectors and giving the collection name. So in this case, we're saying download vectors, product display name standalone, and this is interesting. So we've downloaded, and it's 44,000 vectors. So one for each product. And now they have, it was just one column of text. Now they are 768 dimensions. So, and when we take a look at it, what the vectors are, this is it. There are 768 numbers, some positive, some negative, and they now represent your products. So, and this is quite interesting, because why would you transform your raw data that you can read, that you can understand, into a bunch of 700 numbers that if you take a look at it, it doesn't really make any sense. So why would you do that? Well, the thing is when you take a look at those names up here, sorry to keep scrolling, but when you take a look at this product name, this raw text, we as humans can read them and can understand that this is a turtle check man, navy blue shirt, and I understand what is blue, I understand what is shirt, and this is a casual shoe. But inside computers, machines, algorithms, how can we compare strings? How can we compare products? How can we relate products? How can we say, these two products are shoes, or these two products are shirts? And this is very tough for computers. So you end up writing a lot of code and a lot of hand-tuned rules to use tags. You use all sort of artifacts or hacky ways to categorize and make sure that the computer's sorting and comparing products in the right way. But this is not natural. It's not a natural way for computers to do that, right? So if we wanted to do that using the raw string, we'll have to kind of come up with creative ideas on how to make products comparable, and that's very hacky. That's not stable. And when we think that new data will come in, and maybe other softwares will insert data into your database, and this kind of comparison is very important for your e-commerce or your app or your operation. It's very hard to guarantee that this comparison performance will keep up or will scale, right? And that's the key thing when we think about building a solution instead of building a proof of concept or building just something nice. We want something that's reliable, that is stable, that will scale, and also that is kind of future-proof. So we want to just, we want to grow our business. If we have a fashion business, we want to grow it, we want to scale it, and we want to just, get more data, get more products in as fast as possible. And I don't want to, grow thinking that, someone's gonna insert a product and call it, the bluish jeans instead of blue, and the whole thing will crash. Or someone will say the Puma man gray T-shirt, but you forget to use the hyphen here, and everything will crash, and the similarity search will stop working and stop indexing new products. So this kind of worries, I don't think that we should have in the future if we're dealing with AI and we're dealing with smart applications in production. So I don't think that we should worry about that. And that's why we convert things into numbers, because making math and summing and comparing numbers, that's something that computers can do efficiently, natively, and they were built for that. So every machine learning algorithm, they can only work with numbers. And then our main question becomes what's the best way to convert strings or words into numbers? What is the most meaningful way to do that? And that's what we have built into J. So in this case, we have used this huge pre-trained natural language model to transform those words into meaningful vectors. And when I say meaningful vectors, I mean if we're going to transform it for this, we can't visualize a 700 dimensions, so we are going to perform a dimensionality reduction, and this is only need for our educational purpose here. You don't need to do that in production, but we're transforming that into two components so that we can visualize it in a 2-axis chart. So as you can see here, we have reduced it. It's now 44,000 products with 2 dimensions. We're going to retrieve the IDs just to make sure that we have the right indexing. And Oh, and we are, we encoded into J just the product name. But for visualization purposes, we are merging it with the full product data set, with the full data attributes, so that we can visualize them better and take a look at the product, but also its category and its other attributes, so that we can understand if this worked. So we're plotting here the products, and this is so nice. So what we're seeing here, well, we're seeing that even though we only send to J the product name, when we plot those vectors and we color them by the master category, they, similar category items are close together in this vector space, in this product space that now is hosted on J. So this is hosted on J, right? Your vectors, they are no longer in your computer, they are on J. They are hosted, they're online, they're available for you to query and use them anywhere from any computer. And what I mean is that, Nike men's race day green t-shirt is next to Adidas man printed yellow t-shirt and woman another t-shirt. So these earrings are also close to each other. Those watches are close to each other, and even makeup. Makeup items are close to each other, and I mean, we didn't have to explicitly write those rules. We didn't have to say, a shoe is similar to a sandals, which is similar to slipper. So if you think about it, this is very powerful, not because this works as an algorithm to extract information from our data, but this works as an AI application, right? This works as something that you can put into production online and then use it as a normal application, use it as a solution. It's not something that you have to keep fiddling around and tweaking and turning and testing and thinking about it. Will it scale? Will it work? So, it's already working. So, and I don't even know, this is a kurta, it's a very specific kind of clothing. It's, and even if I don't understand what a kurta is, this vector representation has already understand it. So, and then when we think about our main task here, which is to retrieve similar items and show it in an app, in an e-commerce or something like that, the whole complex task of querying similar items just became a matter of querying closer items in this product space. So when we come here to the next session, which is to perform the similarity search, in reality, what we'll be doing is given a query, say the Nike Man Air Rift. So if this is my query, this is the item I'm looking for similars. All I have to do is look into this product space, and I really mean it, in this like geometric space, and retrieve similar items that are close to this point, to this item, and this distance calculation, and I really mean it, it's a Euclidean distance calculation. It's something that computers, particularly modern computers, can do very, very efficiently in parallel with threaded execution. So it's not running anymore through a deep learning model. It's running directly on this product space and doing this efficiently approximate nearest neighbor search. And when we do that, and of course J will perform this search for you by using the JSimilar method. And that's it. I mean, you call the JSimilar, you say the collection name and the data that you're looking for. So in this case, just for the sake of demo, we ask J to bring the 5 most similar products to each one of the products in the index. So that's why we send here the index. So basically we're saying for all 40,000 products, bring us the 5 most similar. And it's not written here 5, it's the default for JSimilar. So if we want to change that, we just had to write here top K equals, I don't know, 10 or 20 or 100, it doesn't matter. But right now we have run here the JSimilar using the default, which is top K equals 5. So we're bringing the 5 most similar items of the query. So and indexing it back to the original full data frame, which we are doing here. We can see that this is what have been encoded. So we're querying for, in this case, the Nike Man Air Rift. This is our query. So and the query always is also in the answer, because the distance from the query from itself is 0. So it's the top answer. The distance is 0. It's itself, and this is the 4 most similar items that comes after it. So you can see that they are indeed very similar. So this is the Nike Man Air Max, white casual. They're all Nike. They're all Man Air casual shoes. And you can see this is shoes. This says shoe. This is shoes. It doesn't matter, right? So because it's the concept of casual and shoes, and not the singular or plural of the word itself. It's not the single character. It's the meaning that has been encoded. And just for the sake of comparison, although we have only sent the product name, we are displaying here the other attributes, so we can take a look at them and see that the items that were retrieved are really similar to each other. So. But this item had already been inserted into J. So this Nike Man Air Rift, it was already in the collection. So we can send any ID and search for similar products that were inside the collection just by sending their ID. But what we can also do, of course, is query for new items that weren't in the original data frame. So that's what we are doing here with this new product data frame. So we are creating a data frame that we are calling the product display name as well. And this is important. So you have to name your column from the data frame the same way that your previous ones, the original one, was named. But instead of saying an ID that we want to query, we are saying just the name of the product. So we're saying Ray-Ban aviation glasses. So we're not saying the right name is maybe it's aviator and it's sunglasses. So but we're just saying Ray-Ban aviation glasses. And this is the thing, if other software or other vendors are integrating with your system, you can't guarantee that they have the same naming standards that you do. So that's what we want, right? We want a stable, robust systems that can work with new data and new naming standards. So we're using this, and the method is really the same. So we're saying JSimilar for the product display name standalone, which is the name of our collection, and we are sending this new data frame data into J, so we can query for or 5 similar products. So in the same way, we are indexing it back to the original data frame. And this time, because this is a new product that we are querying, it is not already on the collection, so it's not being it's not the first answer. So there's not a distance 0 answer. So we really have now 5 similar products that comes from the answer. So as you can see, even though we wrote Ray-Ban aviation glasses, you know, the context, the similarity search works. And by the way, when we send this string inside J, this Ray-Ban aviation glasses got turned into a vector and then performed the similarity distance search inside that product collection space, and we are bringing the closest one. So the Ray-Ban Man Aviator Steel sunglasses, as you can see, those are, and by the way, those are probably duplicated items, but it's okay. We query them. We have also this Ray-Ban Aviator sunglasses that's not steel, and you know, it works. And notice that we have performed a query here. We have performed this new product name query. We brought, you know, we had the answers here, but we haven't added a new product to our collection. This was just a query. So we just got our answers and we're happy about it. Now, if we wanted to add a new product to our index, all we had to do is to you know, first, you know, just make sure that what's the IDs that are inside J. This is just a little note on that, is that, you know, J won't let you have duplicated IDs in your collection. So as I said before, the collection IDs are very important for identifying and indexing your data inside J. So we won't let you upload duplicated values, duplicated IDs, but you are in charge of choosing your IDs. So we won't do any auto increment thing for you. You really have to just, you know, check already inserted IDs with JIDs and then choose your ID for your new product. So in this case, as we didn't have the ID 0 in our collection, it started on 1163. We are inserting our new product with ID 0. So remember that we are using pandas index R as our ID when we insert data into J. So in this case, we are inserting the Ray-Ban aviation glasses with the ID equals 0. And to do that, it's again quite simple. We're just going for j.addData with the name of the collection, which is product display name standalone, and we are sending this data frame as data in our method. And when we do that, this, you know, this product name data gets transformed into a vector and then stored in our collection. And now, if we query again for the IDs, we can see that it is now added, and it says, you know, the ID now starts at 0 and not at 1163 anymore. So it was correctly inserted on J. And if we query again, so, you know, and this is interesting. So because we inserted a new product into J and we inserted only the product name, so we inserted the Ray-Ban aviation glasses, but our full product table had more attributes such as gender, the master category, the subcategory, article type, base color, season, year, and usage, right? So we don't have that information. We only had the name, which is the Ray-Ban aviation glasses. There are several ways to fix that with J. For this demo right now, we're only going to use the most straightforward and simple method, which is now that this product has already been inserted into J, so it has an ID which is 0, we can just perform a J similar on the product display name. So this is our collection name, and we're sending the product ID, which is 0, as we have inserted it, and then we can query for the similar products that were inserted into J. And as you can see now, the new product itself came as the first answer because the distance to itself is 0, and we can just use it to fill in the blanks with the most similar item. So that's what we're doing here. We're just saying, get the most similar item on our similarity search query and copy its attributes. And by doing that, this is a really, really quick and fast and kind of reliable, not perfect, but reliable way of filling in the blanks of your data. So, of course, if this is in production, I would add at least a flag saying these attributes were filled on a similarity query basis. It's not 100% trustable, but it's better. Maybe it's better than just leaving it if it's not mission critical. If it's not super important to have this perfect, we can fill in the blanks with the most similar items and keep the business going until we have something better. Even with J, there are better ways of doing that. We could have trained separate models to predict each one of those attributes based on the product name, and then we would predict the gender, predict the master category, the subcategory, and so on. In this case, the result probably would be the same, but it would have been more reliable and more efficient, but that's much more complex, and we're not doing that in this demo. Another option for you to visualize your data representations is to use the Tensorboard projector. For this particular demo, we have already hosted the Tensorboard projector tensors. So if we click here, it will load the Tensorboard. This is hosted by the TensorFlow team. It's an awesome tool. So right now it is fetching from our GitHub the vectors, which is a tensor is a multidimensional vector. So they are fetching the tensors, which is exactly the same as the j.download vectors. So it's the same numbers. It is fetching here. It's gonna take some minutes, so we're just keep going for demo. But it's a very nice way of navigating into 3D embedding space and seeing similar items. So we'll leave the link here, and you can later play with it. It's very interesting. And for our last thing here in this demo, so we have created this J collection with the fashion items. We perform a similarity search using Python SDK. Now what we want to do is do the same thing but using the REST API, so that you can integrate basically with anything else that you want. You don't need to be constrained in the Python environment. So what we'll be doing here is you need your collection name as always. You need to provide a notification header using your auth key. This is standard. The first way to use similarity search with REST API using the get method. So the get method, you send your query parameters or the ID of the product that you're querying, and you send it in the URL. That's how the get method works. So you have this base URL, it's always the same. It's mycelia azureapi.net/similar/id, because you're searching using IDs, and you're sending the collection name is part of the URL. And I'm using the requests library here in Python, so that's why I'm using this query parameters here as a parameter for this request, the get method. But in reality, what the request library is doing is adding in the URL these parameters here. So we'll also show you in the Postman, but this is basically part of the URL as any other get method. So that's it. I mean, we're sending this get request to the base URL, sending the query parameters, the ID that we're searching, how many answers, how many similars do we want, and the authentication header. So when we do that and we convert back the results to JSON, this is what you have. So remember, J doesn't keep your raw data. J only keeps your IDs and your vectors representation. So we're querying here. So this is your ID that you're sent as your query. This is your answer. So it's itself with the distance 0. And remember that we talked about distance. This is really distance between points in the product space. So this is yourself, the query itself, and this is the most similar items on that we're bringing back. So you can also use this distance as kind of a threshold on diversification. So I can only show products that are at most at this distance, or I want to show products that are beyond this distance because I want to show different products. This is a single metric that measures how similar or dissimilar your products are, or your items in general. So as you can see, we have the results are here. We are indexing back into the full data frame for a comparison purpose, and as you can see, it's exactly the same result of the Python SDK. But the GET request has a limitation, which is as the query parameters are being stacked and concatenated on the URL. The thing is that you can't query that much items at the same time using the GET method. So that's why we also have a put method where the IDs that you are querying, the products that you're bringing, the similars, they get into the body of the request, and here it's basically no limit on how many IDs you can query simultaneously. So for this as an example, we're just querying 2, but you can query thousands and tens of thousands of IDs at the same time. And this is actually much more efficient because, as I said before, those distance calculations are done in parallel, so you can send it as many as you want, and it will be queried very, very efficiently in our backend. So it's basically the same base URL. The collection name is still part of the URL, and you're performing the request, a put request to the base URL. You're sending, now only the top K parameter is also URL parameter, and you're sending this list of IDs as a JSON body, and also the auth header. So this, in the same way, we have here our answers. Please note that we have one answer per query ID. So we have the answers for the Nike man, but we also have the answers for our second query ID, which is this Ray-Ban sunglasses. And similarly, for as we have done it on the Python SDK on the REST API, we can also perform queries for new products. So it's basically the same. We only need to transform it into a JSON for performing this similarity search. So this is what the JSON query looks like. You need to have an ID and also the product display name. This name should match the original data frame name that we have sent it before. And once we do that, we just put in the collection name, the authentication header, the query parameters on how many similars do we want, and we just send it to the it's not the same base URL, it's slightly different. So it's /similar/data and it's not /ID, because we are querying data here and we are sending your raw data first through a pre-trained model to extract its vector, and then we are performing the similarity search. So that's why the path is slightly different. And here, of course, you need to perform a put and not a get, because you need to send your original data through the body. So we're sending to the base URL. We're sending this list of dictionaries that we want to query as a JSON, and the auth header, and then when we transform the results, we get the JSON of the results. It's exactly the same. So we're bringing here the results, and notice that because probably those are duplicated items, they have exactly the same distance. So this is kind of a byproduct of using J, and you can really spot duplicated or very, very similar items really, really easily. So this is a nice way of doing that. Very, very clean. Very centered on a single metric. It's very easy to use. And that's it. I mean, if this is working on a REST API, then you can just integrate and use it with any kind of software, really. So we can deploy it as a Streamlet app. So Streamlet is basically just Python, an easy way to use Python to build a web application, right? So I don't really code front end, and so Streamlet is really easy and nice way of showing things visually. So this is the fashion demo running on Streamlet. We have this is the J collection, and we can just select any product ID over here, and just let me get myself up here. So we want to run our similarity search for this shoe. And then J will bring similar shoes. So, and of course, if you want to, have not 5 but 10 shoes, we just have to increase our top K and have more of them. Right. So what I want to show you guys is that this is actually the Python code for this Streamlet application. So it's not on the scope of this demo to really write this top down, but basically this is Streamlet. There is nothing new here. And what I want to show is that inside Streamlet, what we're really doing is, there's nothing different than the Jfit, the JSimilar, and the JPredict method. So inside this Streamlet app, what we have is, after all the boilerplate code and create this menu, the button, and loading the image, the similarity search part of it, it's already done when we ended up running the Jfit. So to use that, we only have to get the ID from the select box and run a JSimilar against our collection name with the query data and having, with the top K parameter also. So once you have your data inside J and it gets transformed into vectors, and you perform some similarity search and you check that, that product space or that customer space or that, whatever data you have inserted into J, and it's close to each other, so that J have captured its meaning. Once that's done, it's really a matter of just calling JSimilar on whatever application you have, either by Python SDK or by REST API. So it's really that simple. So we have inside this Streamlet application our auth key, and we created a J instance, and we are now performing JSimilar. So that's how we create this very nice application. And this could have, this could be in your JavaScript application, or really anything else. So we could create different kinds of applications in different languages, and this part of the problem is already solved. It's done. So when we say J is the easiest way for developers to build an application, that's what we mean by that. It's you're focusing on building your application, your solution, and you're not focused on making the TensorFlow works or the PyTorch works, or trying to figure out your hyperparameters, or trying to make things work and debugging those very, very complex machine learning frameworks. So we're really focusing on, here's my data, I'll send it to J. So the whole infrastructure is running on J, the GPUs, the endpoint, the security, the scalability, it's all being taken care by J. So you don't really have to think about it. And you have your working AI application really, really fast. And we have only focused on text here and on similarity search. So we'll have more demos coming, and we'll show you how to do that with image, with table data, and with other kinds of data. But it's basically the same process. Just a little spoiler alert. So it's basically the same. It's always Jfit, it's always JSimilar, and always JPredict. On the screen right now, I just wanted to end this demo running the Tensorboard projector. I think it's very nice and very cool to kind of navigate in 3D through your data, and I think that's very it helps our head get along with the fact that raw data turns into something more interesting than words or categories or table data, and it turns into vectors, and they relate to each other in this latent space, or this semantic space. So I'll stop here just so as to show. So perfumes are already close to each other, and makeup, this shoes. So I think it's very cool to kind of navigate those product clusters, brand clusters, and category clusters, and I think it's super nice to notice that your data has structure, and you don't need to hand write code to manual, keep creative thinking on how to extract patterns on your data. It's, let the machine do its job, let the machine work for you in this sense. So, and this is the very last example of the API being run in the Postman. So just to show it that it works that way too. I hope you guys enjoyed this video. It's a it's an hour right now. Hope you guys enjoyed. I'm certainly enjoyed using J. I really like using this platform. It's really awesome. Hope you guys check also the next demos and our other materials. Generate your key, try for yourself, join our Slack, let us know if you have any questions and suggestions. J is gonna be open source in the future. So thank you all. Bye.